All right, so the recording has started. So let me just quickly show you how to set up the lab. Now, this is something that you don't have to do immediately right away. You can do it at your own time whenever you feel like. You just head over to this particular link, and the link will be in the slide deck. I'll share the slide deck with you after today's session. So you can go ahead here and use git clone to just clone this repository. So you just copy this URL and go to your terminal. Wherever you want to do it, just do git clone and then put that link here. If you don't have Git installed, you can just directly download it as a zip and then unpack that zip file. Okay. So this lab utilizes container-based COS images. Now, it's not necessary that you have to use them. You can use normal hardware switches as well. All you need to do is make sure the switches are configured. It's basic configurations like GNMI and netconf and restconf. So if you want to view the sample configs, you can go into Arista Lab COS, and this is the configuration that you'll have to dump on any hardware switch if you're trying to do the lab using hardware devices. Okay, so just copy paste and dump this particular section, and you would be good to go. Okay, now if you are using the lab, this particular lab itself, what you can do is you need to install Docker. So how you can install Docker is go to your Intelligent Hub, and from Intelligent Hub, you'll see there are multiple apps which are there. And it is taking age. Yeah. So just click on Docker and install it. Once Docker is installed, you can launch it like this so that your Docker engine is up and running. Now, once Docker engine is up and running, you can just directly use the lab. In case if you're not using Docker, there is one more thing about installing all the requirements manually. So yeah, so these are the requirements that you have to install. Again, you can install them natively on your MacBook SR. Just do Python 3 -m pip install and just install these requirements. So if you're not using Docker, you can manually install these requirements and use hardware devices. That's also fine. With Docker, it becomes a bit more easier. All you have to do is once you have cloned the repository. So for example, I have cloned the repository out here. I have all the files here. I'll just go and open VS Code here. Okay, VS Code opens. I close this. Okay, you can see all the files here and just open your command palette from here. Command Shift P and say reopen in container. So basically what it does is it starts a dev container. Now that dev container will install all the requirements that you need for the lab. That includes all these requirements mentioned in this text files. It will also install container lab using which you can start container lab images. Okay. In case if you're using COS on Mac, you would need the Arista COS image, which is for ARM architecture, because normal COS lab image won't work. How do you get it? Go to arista.com, support, software downloads, come down to COS lab, expand 434. We can choose any of these EFT3. The ARM image is still EFT, but you can still use it. So just download this particular file. And to import it, the command is mentioned out here. So all you need to do is just Docker import, give the tar file name and whatever tag you want to specify. Once that is done, you will basically have your Arista COS ARM image loaded into your Docker image repository. All right. All right. So let's start now. We'll start to talk about what is OpenConfig, just to get a basic understanding of what it means. So think of OpenConfig as a open source effort by network operators themselves with the goal to develop programmatic interfaces and tools for managing network. Now, the key point here in OpenConfig is making this vendor neutral and model driven. We'll talk about what that means in next few minutes. Try to think OpenConfig as a universal translator to talk to different network devices, right? So one particular challenge that we keep on facing with network automation is that it's basically hard, right? Now, if you have only dealt with Arista devices, you are pretty familiar how good the CLI is, how good the API is. But if I tell you to, okay, now go ahead and configure the same thing on a different vendor device, you have to learn their CLI. You have to understand if you're doing it via API, you have to understand how their API works, right? So you might ask, okay, every vendor implements a CLI, but at the end of the day, you're doing the same thing, right? If I ask you to bring up a BGP neighborship between, say, Arista and a Cisco device, BGP is a standard, right? But how do you configure the device varies because every vendor has their own CLI. And vendor CLIs are different, not just in terms of configuration, but also operational state. So for example, if you see, I have a BGP session information from a network device. This is a Arista device. So you can see show IP BGP summary, which is pretty familiar that you would typically see. I would see the neighbor IP, the states, prefixes, all the details, right? Now this BGP session has been established with a Nokia SR Linux router. And if you run the same command, first difference you would see immediately is the show command syntax itself is different. So you have to learn or basically try to get to know from the documentation, okay, what are the show commands? And even when you run the show commands, the way the CLI will present you the output is going to be different because every vendor implements the CLI in a different way, right? And this is just operational state, meaning what is the state of certain things which are running on the device? How about configuration state? So when we start talking about configuration state, that is also very different. So if you're, again, you guys are familiar with the Arista COS CLI, right? So you know that BGP configuration typically looks like this, and it is pretty straightforward, right? You just go into router BGP, give the AS number, router ID, neighbor IP, neighbor AS, and you're done. But the same configuration on a Nokia SR Linux router looks like this. So right off the bat, you can see how much different the vendor CLIs are. So even a simple job of telling that, okay, bring up BGP neighborship between an Arista and a Nokia device seems very simple at start. But the challenges which are involved are very hard. You have different configuration syntax, you have different CLIs. The vendor has different commands for configuring the same information. And even when you do configure the device, the operational state is very different, right? So for that, let's actually go back to our lab and try to spin up this lab. So there is this multi-vendor lab out here which you can use. So if you're using dev container, all you have to do is open this particular file here, click on deploy. So it will start up the lab where it will basically bring up a COS lab instance and a Nokia SR Linux router and connect them via a single link. And based on the configuration, it will bring up BGP between those two nodes. Okay, let's give that some time to start. You can see, yep, the COS lab is up and the SR Linux router lab is also up. Now, if you want to connect to this, all you have to do is just go to this container lab icon. Again, this, if you're using the dev container, all of this will already be installed. You don't have to worry about it. If you want to view the graph of the topology, you can see it like this. So this is the topology. You have the COS connected to SR Linux router. Let's actually SSH into COS lab first. Oh, this is SR Linux. Right. Is the font visible? Are you guys able to see it, or do you want me to increase the font size?
A little bit, if you can increase.
Okay. Is it good?
Yeah.
All right. So yeah, you can see this is a COS lab, software image 434. And if we check the LLDP neighbors, it is connected to a Nokia router. So LLDP neighbors detail. Yeah, Nokia SR Linux. To run sec BGP. So we are quite familiar about how BGP looks on our end, the configuration of to bring up BGP. And if I do show IP BGP summary, that is also pretty simple, right? Because we are familiar with this particular syntax. Even if I ask you to, hey, go and check the route. So you do show IP route detail. And you can see, okay, I have a BGP route which I'm getting from my peer, which is the Nokia side. So this must be likely a loop back on the other side. Now, if I go ahead and check the same state on this device, if I had to check the LLDP, first of all, the command itself is very different. So it's show system LLDP neighbor. At the end of the day, you are checking the same information, you're using the same protocols, but how the vendor is implementing the CLI, both in terms of configuration and operational state, is very different. Like, for example, if I ask you to check the BGP neighborship on this site, you'd have to use something like show network instance, default protocols, BGP neighbor. And you can see that this is the peer. It's an IBGP peering, and it is an established state, which is quite similar to what you see out here as well. But how Arista represents that information via the CLI and how this vendor represents that information is very different. And that goes for the configuration as well. So you can see info from running config, network instance, default protocols, BGP. So you can see the BGP configuration is also very different. All right. So coming back to our point, if we were to do this configuration manually, and this is what we have been doing for a very long time, it is still doable, right? Humans can learn that configuration syntax of different vendors, different CLIs, and try to basically get that job done. But if you were trying to do it via network automation, like back in the day of if you're talking about screen scraping using, SSH, it is still a difficult job because you would have to build parsers for each and every different vendor. You would have to build a parser. So, for example, if I give you an automation job of, hey, build me a network automation script, which basically connects to all my devices in the network and gives me an information whether a BGP neighbor is established or not. We're like, oh, that's pretty easy. What type of vendors do you have? Well, I have Arista, well, I have Cisco, I have Juniper, I have this Nokia guys. So then you go and check the CLIs and you say, oh, the information I'm looking for is standard, but how every vendor is showing that information is really different. So you have to build parsers for each and every one of those devices, right? So these are some of the challenges that we typically face with CLI. So in network automation, using CLI is something very hard. So you might say, okay, what about some other options that we have? Well, we have SNMP. Typically, you would say that, okay, yeah, SNMP is something which is a standard where you would have certain MIBs and all the vendors would implement those MIBs, right? But is it something that we can use for network automation from end to end? Like, can I use SNMP for configuring BGP? Well, there are certain set operations which are there, but they are seldom used. And the amount of complexity or complex operations that we can perform with them is very limited. Then is the point of monitoring. When you're monitoring any device using SNMP, you typically do it at a pole-based interval, right? So if I have to monitor the status of an interface, if I set my polling interval for 1 minute, I only get to see the state of that interface at every 1 minute interval. If the interface goes up and down in between that interval, I never get to know about that. And that goes for counters, that goes for routes, any information which can or which is happening between your polling cycles, you will tend to miss. So SNMP, though, is there. It has been there for a very long time, and I'm pretty sure it'll be there for a very more long time. But it has a lot of problems with it. Some of the fundamental problems are these, like having a loss of visibility between the polling cycles, not having enough complexity in it to be able to use to configure devices the way we do today, or the amount of features that we require today. Right. And again, they were not really, SNMP was never really meant for handling bulk data as well. So for example, if I have a router with internet scale routing table, and if I ask you to, hey, pull the device for all the routes that are which are there, using again a network automation, doing that with SNMP is really hard. And OIDs were never user friendly. You had OIDs which were like long dotted number strings, and then you had to use SNMP translate to understand, okay, what that particular OID means, right? So these are some of the challenges which we had with SNMP. Then you might say, okay, the software industry has involved, and along with that, a lot of network vendor devices are also exposing APIs, right? So I'm pretty sure APIs should be the way to solve this problem, right? We should have different vendors, like, for example, Arista exposes eAPI, right? So don't other vendors also expose certain form of APIs? And if they are exposing APIs, we should still be able to get data in a consistent manner, like the same example that we saw before, right? Regarding the BGP status. If the Nokia guys are exposing the CLI in this manner and Arista is exposing it in this manner, what about APIs? Do they expose any APIs where I can connect them using curl or wget or a web page to see, okay, what information is getting returned? So that is true. certain APIs would have, return the data in a different encoding, like JSON format. Then you might like, okay, that's good. But you might have certain vendors who would return the same data in an XML format. So now you have again the same problem of different vendors implementing their APIs in different ways. One vendor might return you data in JSON format, the other might return to you in XML format. And even if you might have certain vendor returning the data in JSON, it will be different in which how it is being structured. So for example, if you see here, this is from one of the Arista devices, how the data is structured within this JSON format is different to how it is structured here. Let's take an example from our lab itself. So we have, again, these two devices. We have show management API. Oh, not this guy. Show management API HTTP commands. So you can see we expose the eAPI here. It's a web endpoint using which we can connect it to. And Nokia also exposes a similar endpoint. So let's take an example of try to pull the BGP information again from both these devices using curl, right? So ideally, both should be able to connect over HTTP or HTTPS endpoint and should be able to return data in JSON format, right? Okay, so for that, we'll go into our demos folder and let's go into intro demo. Okay. All right. So this is the curl command. Again, this is in the README file, which will be there on the GitHub. So whatever demos that I'm showing you out here, all the commands are in this particular lab. Okay. So if you want to try this out at a later point by yourself, you can do that. So let's copy this command and put it out here. So first we'll try out the command for Arista device. So we'll check how that output looks like. Oh, all right. Sorry. Okay, so if you see, we are pulling the BGP information using eAPI, and we are getting the same information regarding the peer address, what is the peer AS, what is the router ID, what VRF it is in, and the information is coming to us in JSON format. So that looks good, right? I mean, you can say that, okay, I can make a Python script, I can get this JSON data, and I should be able to consume this. And I should be able to make a similar script for Nokia also, where I connect it over an HTTP or HTTPS endpoint, and it should give me a data in similar format. And that is correct. So if you connect to the Nokia guys as well, and to run the same request, again, fetching the same information regarding BGP, you can see they're giving us this information in JSON format itself, but how the data is structured is vastly different. So if you see how data looks like for EOS, we start with a key regarding results, VRF, default, peer list. And here we are starting with results, neighbor info, and network instance. So again, even though we have APIs exposed by different vendors, how they are representing the information is different. So again, the same pitfall comes as of CLI as well. If I had to build a network automation for getting information via APIs, I'm running into the same problem of different vendors implementing it in a different way. So why did we talk about all of this? So if you see at the end of the day, as a network operator, what is the challenge that I'm facing? The challenge is I cannot have a network which is just one vendor. I cannot have a data center which is just, okay, just Arista devices or just Cisco devices, just Juniper devices. I will have multiple vendor devices in my network. And it is not at all scalable to be able to both configure and monitor the devices across different vendors in a standard way. If I'm using CLI, for example, I will have to build, do screen scraping and then build different parsers for each and every vendor to be able to consume information or to be able to configure certain states on the device. And that goes for, and SNMP is not a good option because there is a lot of disadvantages there. When we came to APIs, we saw that, okay, different vendors do expose different APIs, but even when they do, they format the data depending upon how they see fit. So I'm getting into the same problem of I have to write different parsers for different vendors. So what if there was a solution? And that's where OpenConfig comes in. So if you see in this particular example, I am getting the interface state counters queried from two different vendor devices. If you see what we are seeing out here is how the data is structured. First is it looks like a dictionary. It is a JSON format. I have keys and values. But what's more important is how the data is represented in terms of how both the vendors are representing the information in a similar manner. Both are saying that, okay, in octets, value is this, in errors, value is this, right? So that's what we are basically trying to achieve with OpenConfig, is where you are setting a standard in terms of how you represent operational states of the device, so that even if I'm pulling the same information from multiple vendor devices, I'm getting it in a consistent format. So I just build one network automation, which is able to query multiple network vendor devices, and all of them return me the information in a standard format so that I don't have to write multiple different parsers or logics to be able to consume that information. And this goes across both configurational state and operational state. By configuration, meaning if I have to configure BGP, I define one model where I say, okay, this is the AS number, this is the peer, this is the router ID. You convert it into your own syntax and configure it and configure the device. And if I'm saying, okay, give me the BGP neighbor statistics, BGP neighbor table, you give me a data in such a format that I'm able to consume it across both the vendor devices or multiple vendor devices. So yeah, what we are solving at the end of the day with OpenConfig is having vendor neutral data models, both for configuration and operational state. By having this vendor neutral model or having a standardized model is basically simplifying our job of network automation, both in terms of configuration, making changes to the network, and also getting states from the network. And the biggest part of it is that it is open source and it is a community driven approach. So as you have more requirements that come in, that, okay, we have a new feature which we need to implement, or basically tomorrow I have a requirement of standardizing, say, IPsec models, right? I want to have a standard way of getting IPsec information from across multiple vendors, or standard way to configure IPsec configuration across multiple vendors. I will develop a model which basically standardizes that, okay, this is how the IPsec data should be represented if I'm getting the operational state, or if I'm configuring it, this is how it should be represented. Again, we'll go into the depth of it, how it is actually done, once we start talking about this in detail. Any doubts or questions till this point? Okay, so again, this is a bit of a theory starting May. It's like with every training, starting May, you will have a bit of a boring theory, but slowly and steadily, we'll start getting into more and more interesting labs. So yeah, just bear through the theory part of it, because again, it is required in terms of understanding certain core concepts. And once we get into those practical concepts, then you can kind of map back to, okay, what you learned in those theory segment parts. So yeah, before I move on to the next segments, any questions, doubts in this part? Just understanding why do we need OpenConfig, or what is the need for that? All right, so I'll take that as no questions, and we'll move on to talking about what is Yang. All right. So Yang is something that you will typically hear a lot whenever you're talking about OpenConfig, or in fact, when you're talking about netconf, restconf, and all these things. So one thing to clarify right off the bat is, if you hear somewhere somebody correlating both Yang and netconf, that's not correct. Yet conf is not same as net. Yang is not same as netconf. Both are two different things. One is a data modeling language, and one is a transport. So netconf, which we'll talk about, will come under transports, and we'll see what that means. Let's talk about Yang first. So Yang, which basically expands for yet another next generation, it is defined as part of RFC 6020, is a data modeling language for configuration and operational state data. So you might ask, okay, what do you mean by data modeling language? Uh, what does that actually mean in practical terms? So one core concept to understand about Yang is it is basically defines how the data should be represented, not the data itself. So for an example, if I ask you to go and configure a VLAN on the device, what would you do? You would ask me, okay, give me the VLAN name and give me the VLAN ID, right? VLAN ID would have to be a number, and it has to be in a specific range. You cannot go ahead and configure a VLAN ID of 1 million, right? Or you cannot go ahead and configure a VLAN ID for, say, ABCD123. right? It has to be a integer, and the name has to be a alphanumeric string, right? Same goes for, say, for example, the MTU on an interface, right? If I ask you to configure an MTU in interface, again, it has to be an integer. It cannot be anything else. And that is what we are defining as part of Yang. So whenever I say that, okay, I have to make a model for defining interface configuration where MTU has to be set, then the modeling language will say that MTU can only be an integer. It cannot be anything else. So it is basically enforcing certain restraints or constrictions around how a particular data needs to be represented. So this is from a configuration point of view. What about operation state? So let's say if I connect to EOS and I say, hey, can you give me a list of all the VLANs? Basically show VLAN, right? So again, if you go back to our lab and we go here and say show VLAN, then this information is basically the VLAN ID and VLAN name. So I have to enforce a way or basically define a model which tells the vendor that if you're returning the VLAN information to the user, the VLAN ID can only be a number and the VLAN name can be an alphanumeric string. You cannot have a VLAN ID which is basically a string, right? So that's what you're basically trying to express as part of Yang, that, okay, I have different models which will define how a particular data should be structured, but not defining what the data itself is. Now, this data can be expressed in multiple different encodings. It could be XML, JSON, and protobufs, which we'll talk about when we come to gRPC. Again, ignore this point for now. We'll come to see how this schema can be represented in different encodings. And you have a lot of different Yang models. You have Yang models for BGP interfaces, even Wi-Fi has a Yang model. You have Yang models for system states, system configurations, and a lot of other details which you'll see. But at a core level, Yang is just a data modeling language. You're basically defining a schema which is telling how a data should look like and some constraints and rules around how that data should be represented. Okay. Any questions, any doubts before we move ahead? Okay, so let's try to look at some Yang models to understand it better, right? Okay, so first we'll take a look at basically try to understand what different types of Yang models are there. Why do we need to talk about this is because that's where your vendor specific and industry models come in. So Yang model definitions can be divided into two major categories. One is your industry standard and one is your vendor specific. Industry standards are defined by your basically standard defining organizations like IETF, or basically groups composed of network operators such as OpenConfig. And vendor specific models are basically something that is native to a particular vendor. That's why you will hear sometimes them being called as native models, or basically those are specific to that vendor's operating system. So Arista will have certain vendor specific models, Cisco will have certain vendor specific models, even Nokia will have certain vendor specific models. There is also an ITF model, basically an ITF version of Yang, but it is very limited in terms of what it can do and configure across different multiple vendors. This is one of the kind of a reason which led to the development of vendor specific Yang models. But again, you ran into the same situation of, okay, IETF has certain Yang models, but the vendor wants to implement a model for something, say BGP or EVPN. But IETF doesn't have that. So vendor goes ahead and implements their vendor specific model. Again, you run into the same problem of different vendors having different models, which is why eventually OpenConfig was created, which is again a Yang standard that is interoperable between multiple vendors while expanding the capabilities of whatever IETF version of Yang which is offered, right? Now for Arista devices, the Yang models are maintained. You can always view them on the device itself and also on the GitHub repository. We'll talk about them in a minute. But the OpenConfig Yang models are available here. So if you go to this OpenConfig public GitHub repository, again, the link is in the slide deck. You can refer to it later on. Maybe go into releases, let's come down to models. You can see there are a lot of different models for different features. You have models for ACLs, BGP. You even have models for firewalls, interfaces, ISIS, LACP, LLDP. You have PTP, QoS. So there are different models for different features using which you can get both configuration states and operational state for a particular device. Again, we basically go down into this a bit in few slides later on. I'm just showing you where you can view the OpenConfig Yang models. All right, let's take a look at some of the Yang models, which will basically give us an understanding of what actually we are talking about. So if you remember, when we are talking about Yang itself, we said that it is a data modeling language which simply says that how the data should be represented. So for example, if I'm talking about defining the MTU on an interface, which is part of the OpenConfig interfaces Yang model, in that MTU says that it has to be a type of unsigned 16-bit integer. It cannot be anything else. So whether you are getting the states from a particular device, that device has to make sure that the MTU is an integer value. Same when you are configuring a device, you can only specify it as an integer. For example, for BGP, you can see the AS number is defined as OCINet AS number, which in turn is again defined as a unsigned 32-bit integer. Okay, so let's go ahead and actually take a look at this interfaces Yang model. And again, we'll talk about some of the, you'll see there is a lot of other details out here. We'll talk about them in a bit, but I'm just showing you the relevant information that we are just starting with. So here you can see it defines leaf MTU. Again, ignore the leaf part. We'll talk about what that means. But it says that the MTU, and there is a description about it as well, says the MTU type has to be a integer only. And uint 16 means unsigned 16-bit integer. It cannot be a float. It cannot be a string. It cannot be any other value other than an integer. So if any vendor is allowing via OpenConfig Yang model to configure a MTU on an interface, you can only configure it as an integer, right? Any questions, any doubts still here? Again, this might be a very different kind of thing that you are trying to learn or go through. So it's okay if you are feeling confused a bit. As we go in with the lab demos, it will actually become a bit more clearer. Okay. If there are no questions, let's talk about Yang models per EOS code. So typically, the Yang models on our switch, you will find them under user share Yang models.
Hey, Himanshu, just a quick question. So Yang,
Yes.
I mean, it's like a guidebook itself, right? As in
Um,
how a particular command should be probably, sent from automation to the device, any vendor specific thing, right?
it's not about how the information should be sent, because that is when we'll talk about transports.
Okay.
You're correct in the terms of mentioning it as a guide. Uh, just try to spin those words off as it's more around defining a schema about how the data should be represented.
Okay.
Okay, so let's say if I'm asking Arista device, hey, give me the output of the your BGP summary table. It has
Right.
to give it to me in a standard format. And the same format has to be followed by any other vendor if I'm querying it using OpenConfig. So if any device says that, okay, I support OpenConfig Yang models, and if I connect to the device using OpenConfig Yang models, and I say, hey, give me the BGP state information, they have to represent that information as per the model so that the consumer of the data doesn't have to worry about, okay, Arista represents information in this way and Juniper represents information in this way.
Okay. So Arista's code also supports Yang. Is that is would it be the right term to say?
You can say that we support OpenConfig Yang models, yes.
Okay.
But
So,
we do also have vendor-specific Yang models as well. We'll talk about this. Yep, sorry, there was one more question.
no, so just to imagine how it looks like, you have SNMP. If you are polling for BGP state, you are going to poll for the same OID.
Right.
In the same way, Yang, you have a defined data structure.
Right. Right.
So the path will be the same. So if you're going to poll for BGP state, it will be the same for any vendor. And in SNMP also, you will have something like a vendor-specific OIDs where you have defined. So the same way, here also Yang will have some native ones. SNMP, you can only poll for information. Here you can configure also.
So what I'm trying to understand is where is you here? Am I on the network automation side, or am I on the side where am I on the device? From the device perspective, I don't know if that question was
Okay,
clear.
so you are the operator. So you are going to poll for the information or send the information to the device.
Okay.
So if it is going to be you need not worry about what is the vendor device in the other side.
Right.
For you, you just need to know the Yang model or like the path. For the same path, it will do the same task for any vendor.
Okay.
Yep. So like Manoj mentioned, try to imagine it as if I have a network, I don't have what my requirement is. I don't have to worry about what all different vendors I have, whether I have Cisco, whether I have Juniper, or whether I have a Nokia. All I want is to configure BGP. Or let's say all I want is to configure an interface with an IP address and an MTU, right?
Okay.
But I don't want to worry about, okay, on Arista, this is the configuration command. On Cisco, this is the configuration command. And on Nokia, this is the configuration command. I don't want to learn or interact with any of those vendor specific things. If those vendors say that they support OpenConfig YANG models, I should be able to define that data, which is according to that model, give it to them, and they configure the devices accordingly.
Understood. Okay. Yeah. Perfect. Now it makes sense.
Yeah, and this goes both ways. So, like Manoj mentioned, with SNMP, typically you would have very rarely seen set operations being used, but the get operation is again consistent across all the vendors. If I give it an OID, they give me the value across different vendors, right? So I don't have to worry about vendor specific OIDs. They are there, but I don't have to worry about that. Same is with OpenConfig as well. If I tell any vendor, hey, give me this counters of an interface, they will format the data or give me the data in this particular format so that I don't have to worry about, okay, oh, this is a Cisco specific or this is Arista specific. For me, I get the counters, I process them both in the consistent manner.
Yeah. Okay.
All right. So that's where you have your OpenConfig YANG models. So OpenConfig is, think of it as a group, like 10 guys got together and they said, okay, let's start a open source project where we will define models for different features so that any vendor who is implementing these models can claim to have support for them. And any user or any operator or any code which is trying to perform those operations for those features can use these models across those vendor devices. So tomorrow, if I install a Arista device, a Cisco device, and a Nokia device, and if I'm trying to bring up an IBGP peering among all three of them, like a BGP peering, mesh peering, right? And if all three of them claim support for OpenConfig YANG models, I can define my BGP configuration as per that model. I can give it to all those three devices, and I should be able to configure them without having to define each and every vendor device configuration individually. Now, that does not mean that OpenConfig YANG models covers each and every feature, which is why you would also have certain vendor-specific YANG models still. That is where your Arista experimental models also come in, and they will be published on this particular website. So this is our GitHub repo, which, oh, not this one, sorry, this one. So for every EOS code, you will see we are publishing certain models, and you will have your OpenConfig public models. So you can see this has, again, all the models which we are talked about, which we saw in the OpenConfig repository. All of those models are defined here as well. And you also have Arista experimental models. So for example, you can see there is a, if you go to OpenConfig YANG models, and if I search for EVPN, there is no EVPN YANG model. So this is where your experimental EOS models comes in, which are Arista specific. Similarly, you will also have other vendor specific models. Cisco will have their own, Nokia will have their own. All right. Now, this is one place to view the Arista YANG models. The other more user-friendly way is go to this particular website. And again, just like you have per release information there, you can view these OpenConfig paths here. Whatever OpenConfig paths are supported on a EOS device, that includes both vendor-specific models, like this Arista experimental models, or standard OpenConfig models. You can see them out here. And again, we'll talk about how to kind of view them and understand these paths in a few minutes. On the device itself, these are present under user share YANG modules. And you can see GitHub OpenConfig, public, release models. These are all OpenConfig models. So on the device, they are present under this particular directory, user share YANG module. So ever if you want to find out, okay, on a Arista switch, where do I find these models defined? You can check this particular path. All right. So let me actually open the OpenConfig interfaces YANG model. All right. So here in this one, Let me increase the size. So you see, there are a lot of different things which are defined in this particular model. So it says OpenConfig interfaces.yang. This is basically the model definition. This will be the file which will be present on the Arista devices itself. So if you go back here, you can see models interfaces. You'll see OpenConfig interfaces. This is the same file which you will find out here. If I do a cat on that file, you see this is the Yang model which we are defining here. Let me actually more. So this is the same file which you'll find present on the device. Now, let's just try to go through some of the very basic things that are defined as part of this particular file. So let's start with the first one, which is the module, which defines what is the name of that particular module. So in this case, since we are checking OpenConfig interfaces, the module name is going to be defined as OpenConfig interfaces. If you're checking something else, like for example, if I open BGP, you will see module name is OpenConfig BGP. So whatever the name of that model is, it will be defined as part of that module. Then comes your Yang version, which is basically defining what is the version of the Yang model for that particular module. You will see versions which are 1.1, 2.2.1, and so on and so forth. So whatever version of that particular Yang model is, it will be mentioned out here, Yang version. Namespace, so think of namespace as something which is very unique for each and every model. And it is mainly used in XML. Think of it as a unique identifier for each and every model. Like in this case, the OpenConfig interfaces, the namespace is defined as this. If you check BGP, it is defined as this. Then you have a prefix. So prefix is basically a short alias. Think of it as you create aliases on your devices, right? So for example, if I have a very long show command, I can create an alias for it. So show IP BGP summary, I can create a alias called SHBGP. So similar way, you have prefixes or aliases that can be created so that if you're using this basically if you're using this particular reference to say, okay, I'm trying to define something in OpenConfig BGP, I can just reference this prefix, and instead of writing this whole OpenConfig BGP everywhere. Right now, one thing to note is that this prefix is only visible inside this module. So it is local to this particular file. If you are defining it somewhere outside, you have to write the full module name. So that's where we'll talk about imports. So if you see imports, if you've ever worked with a programming language, import is one way to import certain data from another class or any function into your particular file, right? So same way with Yang modules is that certain Yang modules will depend upon other modules which are defined. So for example, OpenConfig interfaces need certain data or basically certain types which are defined in IETF interfaces or types, OpenConfig Yang types. So it will import that. And when it is importing, it can define again an alias for that when it is basically importing that particular module. So for example, when we are importing IETF interfaces, instead of writing IETF interfaces everywhere, we will create an alias for it called as IETF-IF. And anywhere within the file where we will call that, we will basically say IETF-IF, right? Okay, so these are imports. Think of imports as similar to your programming languages. You're basically pulling in an external module and just trying to reuse whatever is defined in that module instead of defining everything again and again and again in each and every module. Org is basically just a human name of the body that maintains that module. So in this case, this is OpenConfig working group. If you see the Arista ones, so let me actually go back. Where was it? Yeah. So if you open the Arista specific Yang models, you'll see that experimental, just say EVPN. Yeah, organization is Arista Networks. So whichever is the organization that maintains that module will have their name present out here so that you know who to contact if you want certain feature to be added or something like that. Okay. Next is contact. Again, is the same thing. Basically, who to contact for that particular, basically the maintainers of that particular module. In this case, I think we don't mention contact because we have already mentioned an organization here for Arista specific modules. But for the public ones, you'll see an contact, which will also include a email alias, which is like a mailer group that you can reach out to. Description is just like in Python, you write descriptions for different functions, variables, same way in different models, you can write descriptions, which will define or basically provide certain information about what that particular model does. And coming last, revisions. So think of revisions as updates that you make for the model, but you document also what updates were made and when they were made. So for example, today this model is basically in its state, and tomorrow I want to add any other feature to it, right? So I will update the model, and also I'll add a revision and add a description saying that, okay, what was added as part of that revision. So for example, in this case, this revision has a date and it mentions what is the description for that revision. Basically, it updated that, use single quotes and descriptions. That's it. This is consistent across both OpenConfig models and also Arista-specific models. So for example, if you see EVPN, you have a revision which happened on this date, and it says add support for PPWS MTU, right? So think of revisions as just a history of what all changes were made to that model, and that basically describing what change was done for that particular model. All right, so this part is basically, think of it as a header of a particular model file, and it is information which is like supplementary information regarding the model itself, like revision and the names, namespaces, and imports. Next comes is the actual data definition of what we were talking about, like how the data is supposed to be represented. So for example, if you see, once all this revision part is done, then we actually start with the data definition, where you can see we are defining the interface ID, which has to be type string. And similar way, if you come down, you will have the MTU, which we were talking about earlier, leaf MTU, which has to be a type of integer and unsigned 16-bit integer. So let's try to understand, okay, what is type def, what is leaf, what do these actual value means, or how do I interpret them? So whenever you open any Yang model, which will typically look like this, I've opened the IETF Yang model just because it is a bit smaller and not that complex to understand. So in a model, you will have a tree-like representation. Everything will start with the model name, and within below that, you will see there are different trees, and you will have basically segments. So think of it as a dictionary. You have one parent dictionary. You will have keys. You will have values. Okay, different keys will have a direct value, or they could have sub keys or basically child nodes. Now, in a Yang model, there are four basic types of nodes. You have a leaf node, you have a leaf list node, container node, and a list node. Again, we'll talk about what those are. So let's actually focus on one aspect of it. So we'll just talk about IETF interfaces, and within that, we'll see what each of those things mean. So container node. So container node, again, you don't have to remember all of this stuff. I'm just telling you so that you can later on, when we actually see this representation of data, you have an understanding of what those things actually mean. So container node is basically a grouping. Think of it as a collection of different types of nodes. You could have a leaf node in it, a leaf list node in it. You could have, any type of further nodes that we have defined. So here you can see a container node basically has only leaves. But here in a container node, it has the list, and within that, it also has a subcontainer in it. So think of it as a dictionary. Within a dictionary, you can also have subdictionaries. Now, IETF interfaces has two main container nodes. So if we go back, you have the IETF interfaces and interface state. So interfaces is for configuration of data, and interface state is only for reading the data. Now, one thing that you'll spot right away is that all the nodes within interface states are RO, meaning read only. So interface state is not something which you can configure. It is only something which you can read, which is why everything under interface state container is RO. And only some of the fields which are under interfaces, which is for configuration, are RW, other as RO as well. Again, depending upon the type of the node which it is. So again, container, think of it as a parent dictionary key, which can have multiple child constructs. It could be a list, it could be a dictionary, it could be a value. But at the end of the day, it is basically a grouping construct that is basically used to group different types of nodes. All right, then you have a list node. It is quite similar to how you would have a Python list, just like you have a list in Python, which can have comma separated values of different values. It could be string, integers, and whatnot. Same way, list defines a sequence of list of entries, and it can include any number of elements. That includes sublist, that could also include containers, and that could also include leaves. Leaf list, within that list, there's also a specific type called as a leaf list, which only contains a list of leaf nodes, right? And lastly, you have a leaf node. So leaf node is at the end of the tree. So whenever you're talking about a tree, you would have a key. Within that, you can have a value. That value can again be a dictionary. But at the end of, when you reach that at the end of the tree, you will only have a pair where you have a key and a value. That's what a leaf node is called as. So for example, when you reach the end of the tree in terms of IETF interfaces, then interface and description, this is a leaf node where description only has a value. There is nothing further below this.
So everything is a leaf. There is it, or like I didn't understand the leaf part actually.
So
So
think of, you're talking about this one, right? Leaf node.
yes. So how did we categorize the third line as a description as a leaf? I didn't probably get that.
Okay. So actually, let me explain it using a different example. So whenever you define a dictionary, how do you typically do it? You basically
Yeah.
say,
Yeah.
right? And then I could have a key and a value, right? Or I could have something like a key, but this further again has a dictionary, right? And then within here, you can again have key and value, right?
Right.
So leaf simply means when you're talking about a leaf node, it is basically at the end of the tree, meaning there is no further child to that.
Okay.
So in this particular example, this would be a leaf. This can be categorized as a leaf node, and this one can be categorized as a leaf node. Leaf node.
Okay.
But this guy cannot be a leaf node because this has further children to it.
Right.
Okay. So leaf node simply means that you have reached the end of a particular tree where you only have a key and a value. So when we are talking about this particular model, IETF interfaces, within that we have interface. For every interface, you would have certain leaf nodes which define a key and a value. So for example, the interface name is a leaf node. Similarly, interface description is a leaf node. But when we are talking about statistics, that's not a leaf node. Within statistics, you have further leaf nodes. So in octets is a leaf node. So statistics becomes like a container, which somewhat is similar to this. So this would be statistics. And within that, in octets is a leaf node.
So I was just trying to understand the other lines on that image are also leaves. I mean, if they are a leaf or not. Yeah, I think.
Yeah. So these are all leaves. So whenever
Yeah,
you are reached at the end of the tree, these are all leaf nodes.
understood.
So
Understood.
this column is just defining what is the type of that particular key. So if you see name, it has to be a string. Description, again, has to be a string. And if you see what is the operation status, again, we'll talk about this one. Enabled is a type Boolean,
Yeah.
right? So for example, if I'm fetching data for an interface, it will give the name as a string, but the enabled field will be a Boolean, true or false.
True.
Okay.
Yeah, but all these are leaves, right? The ones which are like intended towards the, I mean, just below the interface.
Yes. So within interface, again, when you start with this first value, for example, like I told you about interface, this is a list, right? But
Right.
within that, you have different leaves. Similar
Understood.
way, statistics is a container. Within that, you have different leaves.
Okay.
Okay. Any other questions, doubts? So
Where are
again,
the permissions defined?
where are the?
Permissions defined?
Oh, you mean in the model itself?
Right. In the young model, I don't see any where we mention the permissions.
One second. Yeah. So you'll typically see something like this defined. So any node which allows a configuration or not will have a config true or false. Okay. All right. Any other questions, queries before we move forward?
Yeah, so I see container list and container, like, yeah, here.
Uh-huh.
So a list can be inside a container?
A list can be inside a container, yes. So if you see when we define container, it is a grouping construct that is basically used to organize related data nodes together, which can be anything, which can be simply a leaf node. It could be a leaf list node or a list node, or even container nodes as well. So think of it as when you define a dictionary, a key in a dictionary could have anything, right? It could have one single value. It could have a list. It could even have a further dictionary, right? So same way, container is just a grouping. All you are saying is that, okay, I am grouping certain things together. Within this, you can put anything. You can either put a container, you can put a list, you can even put a single leaf there. Doesn't matter. Okay. The whole purpose of container is I'm grouping related things together. So for example, if you see the statistics container, the statistics is grouping all the counters together, right? Similar way, a much more parent container, when under IETF interfaces, I'm grouping interface states as one container and interface, which is for configuration, as one container. But within that, you can have multiple things. You could have a list, you could have a container.
So I just want to understand the difference between container and list.
Yeah, so list will become much more clear once we are actually defining the data. So for example, what do you interpret by list? List is something like if I say, give me a list of interfaces. So how would you define that? You would say something like this, ET1, ET2, ET3, right?
Mm.
So same way, whenever you're talking about this particular model, if you see it is having an interface, so interfaces, under interfaces, you will have interface ET1, which will have all these characteristics, all these values. Then again, interface ET2, which will have all these values, ET3, all these values. Once we start to poll, basically get the data from actual nodes, you'll basically understand it better. So let me try to write it in a way. Okay. So if I say IETF, I'm just writing it in a rough format, IETF interfaces, then interface. And if you talk about this particular container, interface state. So interfaces, then you will have interface ET1 and interface state. This will be replicated across multiple interfaces where you will have ET2, ET3, ET4. So if you see, this is interfaces. This is where your list comes in. So if you come across here, interfaces, within interfaces, this interface is actually list. And this is how it would look like. Does that kind of answer your question? Again, once we start pulling data from the devices in those examples, it will make much more sense.
Yeah. So one more thing, Himanshu, for read only, we saw that config is equal to false. But what if we have executable permissions also, like in this example, VCXRO?
RO simply means read a state and RW means read write.
Yeah, man, just because so.
Yeah.
So how do we differentiate leaf nodes and leaf list nodes?
Okay, good question. So if you come here, yeah. So a list node basically defines a sequence of list of entries. So in this case, this list interfaces will have different interfaces like we had defined here, interface ET 1, 2, 3, 4, right? A leaf list node is simply a list of leaf nodes, meaning if you have a list which only contains leaf nodes, then that is called as a leaf list node.
Okay,
Okay.
the example we had, right, for ET1.
Mhm.
Under ET1, we'll have name, description type. So that's going to be a list.
If you have multiple further, so under interface, you would have, like as per this IETF definition, you don't have any further list under this. You will directly have leaf nodes, right? So this whole collection can be called as a leaf list node, which only has a collection of leaves. Because these are all leaves, right? There is no further data structure behind this.
Then, like in this case, both like list node and leaf list is similar, right?
No. So list here is an interface which contains both leaf nodes and a container node. Like for example, if I go back here, if I
Yeah.
say ET1, right? So ET1 within interface state, I have two parts. One is, say, for example, name, and I also have statistics, right? I'm just writing as stats. Now, if you go back here, you can see name is actually a leaf node, right? But what is statistics? Statistics is further a container under which you will have in octets and everything, right? So stats is a container. So in this case, the interface state, this particular whatever interface is this you have, this becomes a list because it contains different types of elements, a leaf and also container. But if you are talking about simply a leaf list node, that cannot have a container. It will only have a list of leaf nodes.
I think probably more examples would make it clearer.
Yes. So again, once, like I said, once we start pulling the data from the device, you will actually be able to understand it in a much better way.
Yeah.
All right. So if we go here and check third-party ITF interfaces, ITF interfaces.yang, it looks like this. So how do we go from this file to something like this, right? Because reading this in itself is not that user-friendly, right? I have to kind of spend a lot of cycles trying to understand, okay, what this represents or how do I interpret it in a much more easier way, right? So how do I get this representation out, right? So this is basically something called as a tree-based representation, which you can use or basically print using a tool called as PyYang. Now, again, there is a lot of things that PyYang tool can do. One of the things is basically representing a tree model for any OpenConfig model that you specify. There are other use cases as well, like converting a Yang model into a Yin module. So Yang, if you see, is in a format of JSON, right? So this representation is called as a Yang representation. If you convert this into XML, that's what we call as Yin. But again, that is something that you don't have to use all the time. So how do we go about and view this tree-based representation, right? So you can use PyYang. In order to use this, you have to install this tool. So again, let's go back to our demo lab. Really close this. Close this. Okay, come here. I'll actually editor area. So that's easier. Okay. Let me actually open this here. Demos. So for PyYang, you can go to the Yang demo. And from here, you can see you need to install PyYang and PyYang bind. So again, like I mentioned, if you're doing this manually, you have to install each of these requirements individually. If you are using a dev container, all of this will come installed by default. So for example, if you see here, I have this installed already. Now I have all the Yang modules, I have put it under this particular folder, which is called as public Yang. So all these files are already here. Let's do a cat. So cat demos, public Yang models, OpenConfig, not AAA. Let's see, interfaces.yang. So this is the file, OpenConfig interfaces Yang file. If I want to see the tree-based representation of it, you can use PyYang. Now the syntax for this is again put in the demo lab. So what you have to do is you can give PyYang -f3 and the path for that. So you can copy this whole thing, paste it here, hit enter, and you can see the entire tree-based representation of this particular Yang module. Now you can do this for any Yang model which is there. So instead of OpenConfig interfaces, let's use OpenConfig system, not boot. So this is the tree-based model for OpenConfig system, which defines a lot of things like host name, domain name, AAA configuration, authorization. You have logging, SSH. So any Yang model file which you have. So I have put all of them under this particular folder, public Yang. you can see the tree-based representation for each and every one of them by just giving this particular command. So py-yang-f tree, and then you basically specify the path where that file lives and whatever file you want to see the tree-based representation for. Okay. Examples are also present in this demo lab. All right. So this is a tree-based representation. There is also something called as a XPath style paths, which is basically gives you representation in this format, right? This is what you typically see on the website here. So if you go to this particular website, arista.com, let's select this. So let's go to OpenConfig interfaces, OC interface, and config, say, yeah. So this is what you see, path. So if you want to see the entire Yang module in this format, which are called as XPath style paths, you can again go back to the same demo. Instead of format as tree, just use its flatten. So let me just copy this command, go back here, do it for OpenConfig interfaces. You can see it like this, right? So you can see we have an entire set of paths for configuration, an entire set of paths only for state. Okay. So these are two ways in which you can interpret or basically read a Yang model in a much more user-friendly way using PyYang, either using the tree format or using the XPath style format, which you can use either using PyYang, or there is another tool called as GNMIC, which will also do the same thing for you. So again, go back, say GNMIC, path, demos, public Yang. What's the one? Let's path and file. File, demos, public Yang, interfaces. Okay. So both of them do the same thing for you. Okay, let's do a time check. 10 minutes remaining. We cover augments and deviations. Okay, let's stop till here then. Because if you go to augmentation, deviation would be way too much. Any questions, any doubts till this part? And again, I understand this is a very new concept or a new thing that you are seeing. In case if you have already have some experience with it, it's good. If you have not any experience with it, just take your time through it. I'll share the slide deck and also you can refer the recording at a later point also. So just go through it. And if you have any questions, queries, you can always reach out. But before we end today's session, any questions or queries?
Can you maybe show that paste bin once more, where you were trying to interpret flattened output, right?
Yes.
Can you go on that once more?
Yeah. So flattened output, let me actually go back and show you the lab example itself. So if you remember, we had the OpenConfig interfaces. Where is it? OpenConfig interfaces. This is man. My eyes are going bad. Okay, so this is the Yang model. Now, if I have to see this Yang model in the tree path, I can just use this command, py-yang tree openconfig interfaces.yang. So this is how it would look like. I'll just copy it. All right, and put it here. Okay, so if you see, again, OpenConfig interfaces has interfaces. Within this will be this is your container, main container. Within this, you have a leaf list. Okay. So this leaf, if you see, contains your state. Again, these are again a container. Within this container, you have different leaf nodes. So if you come, for example, if I have to say, configure the interface name. So you would have path like, you would write the path something like this. You just type it out here. Okay. Interfaces, then interface. Now, since interface is a list, you would need to specify for which exact interface you need to write it. So you would say name is equal to Ethernet 1. And then you would say, okay, what is the name of the interface? Config name. And basically the name of that particular interface. Same, if I had to set MTU, and the value would be an integer value, let's say 9214.
Okay.
Okay. Now this is a tree-based path. Again, if I had to view this in that same path that we were talking about, the flattened out path, you can use the py flatten command. So this one, or you can use the this one, gnmic. So either one you can use, and if you see, it gives you the same information. So OpenConfig interfaces. Yeah. So again, you have interfaces, interface name. So like I was talking about interfaces, interface name, whatever path that you're trying to specify. So for example, MTU, you see it is interfaces, interface name. So if I was defining for a multiple set of interfaces, I would do
Okay.
something like this. Yeah, so here I would just say Ethernet 1. MTU would be whatever value that I am specifying, ET2, then ET3, whatever the value it is, 1500, 1600, or 9214. Okay.
Yeah, understood. Thank you.
Cool. Any other questions, queries? All right. Any doubts about the lab also? Anything you're not clear about? Let me know.